Light is the transmission medium of the future. Large bandwidths and low attenuation over long transmission routes are indisputable plus points for optical waveguide systems. In many industrial problem areas, optical transmission will soon be indispensable because of its flexibility, cost-effectiveness, and lack of susceptibility to interference. Above all, the advent of the microprocessor in plant engineering has created a need for extremely efficient transmission systems. Proven fiber optic techniques are already available for providing future-oriented solutions. However, there's more to optical transmission than the fiber optic cable alone. The complex part of the work is performed at the fiber ends by components such as transmitter and receiver modules, transducers, connectors, waveguide couplers, and relays. These process the modulated light with high precision. This makes optical transmission a versatile, fully integrable system. Process automation in heavy industry requires parameters to be accurately and reliably controlled. However, the presence of high-power machinery exposes process control systems to considerable electromagnetic interference. The reliability of conventional data lines can only be ensured under such conditions by means of elaborate measures for potential equalization. Future trends in power engineering. Nuclear fusion at over 10 million degrees being researched in a test reactor at the Max Planck Institute. A toroidal cage requires millions of amperes in order to generate a magnetic field. Optical waveguides are directly exposed to such fields, but the absence of potential and the resistance to interference which characterize optical transmission make for a reliable data path with no maintenance requirements. Safety is the prime concern of passenger and freight transport systems, and safe rail transport depends on absolute reliability in data transmission. Rapid transit and subway systems already operate with a high degree of automation. Large quantities of data are reliably processed. The control lines for switches and signals are installed near the track where the power conductor lines are also located. But what happens if electromagnetic interference affects the control pulses? In the case of the Trans-Rapid Magnetic Suspension Railway, a German development, state-of-the-art technology has been employed throughout. With railway switch control, for example, all switching paths are formed by optical waveguides. Because the power conductor lines are isolated from the optical data paths, reliability levels are high enough to match the exacting demands of future rail projects. In refineries, dangerous oil vapors and explosive gases are everyday risks in many branches of industry. These risks are monitored by highly elaborate technical facilities. In the chemical and mining industries, explosions caused by sparks present a major risk. Plugging in a live cable can have disastrous consequences, as can short circuits or damaged leads. Optical waveguides are a boon to such areas where a high degree of safety is essential, for the absence of electrical current means that sparks cannot occur. The result, greater safety for people, plant and environment, and higher productivity into the bargain. Another example, high voltage technology. Extreme differences in potential give rise to problems that can be solved using optical waveguides. Besides gate-controlled triggering of thyristors, this particularly affects communications between power supply utilities and transformer plants. The optical fiber cable can be installed alongside the high voltage cable. Data on consumption levels and network faults are accurately transmitted to the central station. This application points up the advantages of potential isolation. Susceptibility to faults and crosstalk are some of the disadvantages of copper cable that are causing increasing problems in electronic data processing. The growing mass of information in large-scale computer systems presents considerable data transport problems for planners of office complexes. How can 200 megabits per second be securely transmitted past the power lines, generators and magnetic fields that lie between the basement and the 20th floor? The extremely high transmission bandwidth and total resistance to interference fields have predestined optical fibers for office communication. One single-mode fiber alone provides in multiplex mode higher capacities than a whole group of flat conductor cables and also obviates the need for shielding. Active security is therefore ensured because of interference resistance. And passive security is also a feature of optical transmission. Data is immune to unauthorized interception. But security is only one aspect of optical fiber technology. Other decisive advantages include low attenuation over extremely long transmission paths, low weight and low space requirements. Optical waveguides go hand in hand with progress achieved in material and system optimization. Leading-edge technology requires high capabilities, reliability and flexibility in data transmission. Optical fiber data lines are now available for all industrial applications. Siemens components provide the vital basis for the versatility and adaptability of these systems. Transmitters and receivers are available for data signaling rates up to 200 megabaud, as are compatible peripheral components for applications in the industrial sector. Sophisticated connectors make for application-oriented handling. A large range of variants provide adaptability to all operating conditions. Connectors for optical waveguides are high-precision components. Their extremely low tolerances mean that maximum accuracy is required during manufacture and inspection. Optoelectronic transducers act as the transmitter and receiver components. These can be tailored to customized configurations. What's more, complete standard modules with V24 interfaces are also available. These cases may look inconspicuous, but they contain the technology of the future. Here, modulated light energy is being generated in step with the applied current for transmission through the optical fibers. This light is then converted back into electrical signals by a demodulator. Optical relays permit changeovers between various signal sources without the need for intermediate electronic components. In ring circuits, relays provide proven reliability. In the event of a defect, they close the transmission circuit and thus keep the combined circuit operational. Couplers and multiplexers are available for complex systems. The product spectrum ranges from simple 3- and 4-port couplers to star couplers, providing 64 connections, for example. All transmitters and receivers are TTL or ECL compatible. V24 interface modules can also be unproblematically integrated into existing systems. The wide variety of possible combinations means that network and bus structures can be tailored to suit individual technical and economic requirements. Optical waveguide technology from Siemens, technology with know-how. Siemens is among the most experienced manufacturers of optical communication cables, components and systems. Technology with reliability. Every single product is the result of thorough research, development and testing. Worldwide service. Siemens agencies handle communication projects in all parts of the world. Optical waveguide technology opens up new dimensions in many fields of application. And Siemens components are there too, making fiber optics a reliable and cost-effective technology for industrial applications. currents up to 50 amps, voltages up to 1000 volts, power electronics. Until recently, a field dominated by thyristors, triacs, and bipolar transistors. But now MOSFETs are here. MOS field effect transistors are taking over in one application after another, replacing or complementing conventional semiconductors. Their standard parameters are just as good as those of bipolars. Additional parameters, which are becoming more and more important, are incomparably better. MOSFET circuits are smaller, quicker, and more reliable than anything so far available. We can see, for example, what progress has been made when we compare this motor control, a conventional circuit with bipolar transistors and no less than 31 further components, with this modern MOSFET circuit, with no more than 4 SIPMOS transistors. But above all, think of the improvements made possible in our everyday lives. At work, the flicker-free monitor. It has been made possible by the high switching frequencies of SIPMOS transistors. For the physically handicapped, the voice-controlled car, now economically feasible through integration of microelectronics and SIPMOS power transistors. Driving, the anti-lock braking system. Safe braking for large and small automobiles. SIPMOS components open up new, so far unknown possibilities. What looks here like an electronic toy shows the possibilities of combining optoelectronics and power electronics. Power electronics will never be the same again. Power MOSFETs are manufactured in silicon planar technology, the same technology used for years for the manufacture of VLSI memories and microprocessors. Thus, Siemens could use its comprehensive microelectronics know-how to develop power electronic components using the most modern MOS technology. The result? SIPMOS. To look at, nothing more than the usual standard packages, but inside, highly developed technology. The core of a SIPMOS transistor is such a silicon chip. This one is mounted and bonded in a TO3 package. Its surface, although only a few square millimeters in area, consists of thousands of cell elements, each one of them a completely functioning microtransistor. All these microtransistors are in turn connected in parallel. Thus, the total current of a SIPMOS transistor is the sum of several thousand microcurrents flowing through the chip. This permits an excellent use of silicon and a very high degree of reliability. The width of such a cell element is only 20 thousandths of a millimeter. In spite of their high power, the SIPMOS microstructures have a packing density which can very well be compared to that of LSI circuits. In principle, the planar layer structure can also be compared to that of LSI circuits. Here is a simplified picture. The basic material is an N-conducting silicon wafer, the substrate. The bottom metallization will later become the drain connection. On the substrate there is a weakly doped N-epitaxial layer, into which the individual cells are implanted. The gate consists of conducting N+ polysilicon and forms a lattice over the surface of the chip. Silicon dioxide insulates the lattice from the epitaxial layer and the metallization on top. This aluminium layer forms the source and at the same time connects all the cells on the chip in parallel. Some details of SIPMOS technology are especially important to achieve the excellent SIPMOS properties.
For example, the sloping edges of the gate are a prerequisite for the self-adjusting process, which is described in detail later on. In addition, these sloping edges provide an excellent base for the aluminium layer, which is applied later. This is an important factor in the reliability of SIPMOS transistors. Special structures have been developed for the edges of the chips. P-conducting guard rings and blocking areas of amorphous silicon ensure stable operation of SIPMOS transistors and prevent voltage breakdowns, in particular as far as high-voltage transistors are concerned. Nowadays, these structures are developed with the help of computer-aided design techniques. Therefore, ultra-modern CAD systems are a matter of course in the SIPMOS Design Center, the birthplace of all SIPMOS transistors. Our engineers use them to develop the complex structures of the various transistor layers. In this modern method of development, all the parameters necessary for the manufacture of a transistor are stored in a data bank. For, useful as these plotted drawings may be for many purposes, paper is of hardly any significance as a basis for production. For example, the data for the centralized mask production are transmitted directly from the SIPMOS data bank to the main computers at the mask center. There is a lot of technological know-how in SIPMOS. A further example. SIPMOS chips are not soldered to the housing, they are epoxy die bonded. The result? Much better temperature cycling stability and increased reliability. Whereas soldered transistors totally failed after only 2,000 to 3,000 temperature cycles in a test, SIPMOS transistors were still functioning without problems after 5,000 cycles. SIPMOS, the leading technology under the surface. The manufacture of a SIPMOS transistor includes several hundred work steps. Most of them take place in a clean room like this, for the number one enemy of chip production is dust. Microfiltered and air-conditioned air flows from so-called laminar boxes and then over every workstation. A grain of dust coming from outside has no chance of advancing against the direction of flow of this clean air into the working areas. Furthermore, the air pressure in the clean rooms is slightly above atmospheric pressure, which largely prevents the penetration of dust at the air intakes. But now let's look at least at some of the numerous steps in the creation of a SIPMOS chip. The starting material, as in IC manufacturing, is high-purity silicon in wafers such as this, of 4 inches in diameter. On each wafer, several hundred SIPMOS chips are manufactured simultaneously. After thorough incoming inspection, the wafers get their first oxide layer. This process is carried out at about 1100 degrees centigrade and takes several hours. This is the result seen under a scanning electron microscope. Now windows have to be etched in the oxide layer, through which the so-called first P-well of the cells can be implanted into the epitaxial layer. For this purpose, the wafers are coated with a light-sensitive photoresist. This centrifuge uniformly distributes the photoresist as an extremely thin layer over the surface of the wafer. This is one of the prerequisites for the great uniformity of the SIPMOS parameters. When the resist has dried, the wafers are exposed through a precise metal mask like this. The structures of the mask with its millions of P-well windows are already so fine that the wafers can no longer be exposed to visible light, and so short-wave ultraviolet rays have to be used. There are alignment crosses on the mask which are also exposed onto the wafers, and which serve to align all further masks exactly. In a photochemical process, all exposed parts are removed from the photoresist layer, whereas those not exposed remain on the wafer. This means, in the photoresist layer, windows are produced with the oxide layer below uncovered. Only at these points can the following etch attack and dissolve the oxide down to the epitaxial layer. This is a cross-section showing the two windows in photoresist layer and in oxide. So the first photolithographic process is finished and the photoresist is removed. Now only the oxide mask covers the epitaxial layer, resistant and dense enough for the doping process which now follows. In the case of SIPMOS, doping is performed using complicated but very precise implantation technology. A considerable amount of equipment is needed for this process. However, it enables particularly exact dosage and very high purity of doping to be achieved all over the wafer. This process takes place almost totally automatically and is computer controlled. Here is how it works. The whole process takes place in a vacuum. The gaseous, electrically charged doping material acts as the ion source. A strong electrical field accelerates the ion flow. Unwanted foreign ions are filtered out in a beam analyzer, and the ion flow is directed by deflectors. The doping atoms finally hit the silicon wafer at a high energy and penetrate its oxide window into the epitaxial layer. This penetration, however, is only superficial. For this reason, the implantation is followed by a diffusion process, in which the dopant atoms are further driven into the epitaxial layer. The first P-well is now ready. Of course, one single P-well does not make a transistor, and so the process described in principle is repeated for each layer of the transistor. And between each step there must always be controls. Controls, controls. A further important step in production is the plasma etching of the polysilicon gate, which also contributes to the consistency of the SIPMOS parameters. The sloping edges of the gate window, which are produced by this technique, ensure that the following P- implantation is a self-adjusting process. The dopant ions penetrate the gate in exactly the concentration permitted by the sloping polysilicon layer. So the P- area being formed in the epitaxial layer is determined, both in its doping levels and its position relative to the gate, directly by the gate itself. Photographs taken under a scanning electron microscope of the P- area in a random selection of cells on a random selection of wafers show a perfect uniformity of all structures. The self-adjusting process is one of the most important reasons why the distribution of parameters is so tight with SIPMOS, and the RDS-on is lower than with all other MOSFET technologies. The production process continues. The total time required for a wafer to undergo all the process steps involved in manufacture is several weeks. As, however, more and more SIPMOS types are being produced in parallel, and in turn many wafers of each type are being manufactured simultaneously, there are always several thousand of them in processing. Thousands of wafers, hundreds of thousands of transistor chips, each one demonstrating tested SIPMOS quality. The breakdown voltage VDS and maximum drain current ID are, besides RDS-on, the parameters to use for orientation, in the transistor selection guides. Devices manufactured using conventional MOSFET technology usually have wide variations in parameters. This means that in addition to the product actually targeted, a number of other types are produced which are not actually needed at all. Quite different in the case of SIPMOS. The superior technology, the highly developed manufacturing process, the strict quality controls, all these make possible a precisely targeted production, with very little variation in any parameters. The SIPMOS product range does not contain products which happen to fall out of the production, but rather products which have been specifically targeted, as required by customers and planned for exactly. And should there be a new application which really requires a new product, we will make it. However, not like this, but like this. SIPMOS transistors, like MOSFETs in general, are competing with bipolar transistors in some applications. Since in the long run an economical solution for the whole circuit is decisive, here are the most important technological advantages of SIPMOS transistors which contribute to reducing circuit costs. Advantage number 1, no so-called second breakdown. The safe operating area of SIPMOS transistors is restricted only by the maximum current, the losses which can be dissipated, and the maximum drain source voltage. In the case of bipolar transistors, however, the second breakdown always leads to this typical significant reduction of the safe operating area. Advantage number 2, the negative temperature coefficient. Whereas in bipolar transistors the current can rise with temperature until the transistor destroys itself, in SIPMOS transistors the current drops with increasing temperature. Especially in switching operations, this leads to higher reliability and longer life of the transistor. Advantage number 3, very low driving power. The very low driving power necessary for SIPMOS transistors permits extremely simple low-power control circuits, whereas current-controlled bipolar transistors need complex driver stages. Since a SIPMOS transistor, furthermore, can switch high currents at the 5-volt outputs typical for microcomputers and LSI circuits, it is a power switch compatible with these ICs. Advantage number 4, the high switching frequency. SIPMOS transistors have practically no storage time. Their switching times are in the nanosecond region. Pulse currents of 10 amps and less than 1 microsecond duration are no problem at all, with, as already mentioned, negligible driving power. When using bipolar transistors, a pulse of 3 microseconds duration can only be obtained with the help of complex circuitry, since a continuous high base current is necessary to turn on in one direction and sweep out the stored charge in the other direction. Developing a suitable circuit which can be mass-produced costs a lot of time and money, much more than a SIPMOS circuit. This brings us to a further economical advantage of SIPMOS, the low circuit development costs for the user. For it is the precisely defined behavior of SIPMOS transistors and their simple drive requirements, often provided by standard circuits, which enable quick and extremely cost-effective circuit development. This alone is the reason why circuits using SIPMOS, even in high volumes, are often cheaper than bipolar circuits. So it is no surprise that exact cost comparisons, taking into account all factors from development to warranty, show a clear competitive edge for SIPMOS in many applications. And even as far as the component alone is concerned, the difference in price caused by the differing technology is becoming smaller and smaller. Even now, the new EconoFETs from the SIPMOS product range compete shoulder to shoulder on price with bipolar transistors of comparable performance. In this case, the price barrier so frequently quoted does not exist anymore. Without doubt, SIPMOS transistors have a great future still ahead. For many inventions that will really revolutionize power electronics through SIPMOS exist on drawing boards only, or in the minds of creative development engineers. Here are some applications showing the possibilities of SIPMOS. This conventional electric welding machine, for instance, weighs 300 kilos. The model to follow using SIPMOS no more than 8 kilos. This means a reduction in weight to nearly 1/40th of its former weight. Solution: high-frequency pulses of the primary current in the welding transformer possible through the high switching frequencies of SIPMOS transistors. The 50 Hz three-phase line current is rectified via silicon diodes and smoothed by means of electrolytic capacitors. With the help of SIPMOS power transistors, the DC voltage of about 500 volts arising from this is cut into a square wave voltage with a frequency of 40 kHz. This impulse voltage feeds the primary winding of the welding transformer. The welding current generated in the secondary winding is rectified by fast silicon diodes and smoothed via a filter choke. Such high-frequency pulsed welding machines have decisive advantages against conventional ones. They are much smaller and lighter. They permit the welding voltage and the welding current to be continuously variable, and thus enable both manual welding and MIG-MAG and TIG welding to be carried out with only one machine. Variations in the line voltage can be stabilized very well. DC current smoothing is simpler, and, not least, the power factor of these devices is so high that primary energy can be saved. A second example: inverter-fed three-phase motors. This three-phase motor has features so far unknown. It can be fed both from the DC line and the single-phase line, with continuously variable speed. It works back and forth, with acceleration and slowing down precisely programmable, and even in top revolutions, this motor is of low noise. Furthermore, it is light and does not need much maintenance. The three-phase sinusoidal current the motor needs is generated by this microcomputer-controlled static frequency changer. The computer program is responsible for the drive for these three SIPMOS half-bridges, in order to chop the DC voltage into square wave pulses with sine wave modulated width. In this circuit, for example, the pulse frequency is 15.6 kHz, corresponding to a fixed sequence of pulses at 64 microsecond intervals. The pulse width is variable in 127 steps, from 63.5 microseconds down to 500 nanoseconds. A pulse width of 500 nanoseconds at 310 volts breakdown voltage, a case for SIPMOS transistors. For only very high switching frequencies permit the generation of such pure sinusoidal current from DC current that a three-phase motor works with no problems over a wide range of speeds and loads. A third example: a switched mode power supply for dimming a low voltage halogen lamp. In contrast to conventional lamp ballasts, this SIPMOS SMPS has an IC-controlled half-bridge circuit. Thus, the working frequency of the device can be altered by a potentiometer over a range of approximately 95 to 215 kHz. Voltage varies between 1.3 and 11.7 volts. The lamp brightness is between 3% and 100%. The efficiency is 88%. The last example shows a view into the near future. This is the wiring system of a modern car, consisting of hundreds of meters of different cables, some centimeters thick and with dozens of branches. In some years, however, the cabling in our cars will have completely changed. For in spite of much more electronics in the car, today's maze of cables will have disappeared. A single three-wire cable, the so-called bus, will lead through the car. Connected to the bus are decentral control units, whose intelligent core is a microcomputer. There are input elements, such as switches, keys, and sensors, which are connected to the computer through the appropriate adaptation hardware. And here are some output elements, lamps, motors, displays, and so on, which are controlled by SIPMOS transistors directly driven from a microcomputer. A serial interface to the bus enables the exchange of information between all other control units. The wiring of cars has turned into a data processing system. A concrete example. The driver flips the switch rear window heating. The control unit addressed processes this information and notes that the rear window heating is to be switched on by a different control unit. It therefore enters the command switch on rear window heating as a code onto the data line of the bus. Although this command is received and checked by all control units, only the correct one will further process it and switch on the rear window heating via a SIPMOS transistor. It is especially valuable that this SIPMOS transistor can automatically recognize any load failures and react to them so that the car driver can immediately be informed about electrical faults. The example multiplex wiring shows one aspect very clearly, the trend toward a merging of microelectronics and power electronics in the future. SIPMOS technology opens many new opportunities, such as the wonder lamp shown at the beginning of this film. It has a completely new MOSFET component in it, a high voltage power switch which is light triggered and called CTAC. Power electronics, SIPMOS.
Optoelectronic components play a very important role in modern electronics. They were decisive in the process of conversion from mechanical to electronic means and still are. Optoelectronic components, by converting electrical signals into optical signals and vice versa, have produced first-time solutions for many applications. A classic example, optoelectronic coupling elements, known as optocouplers for short. Looking more closely, you can see that an optocoupler is a system composed of two elements, a transmitter and a receiver. The arriving electrical signal is converted into an optical one by the transmitter, a diode. This is coupled by a light conducting medium to the receiver, a phototransistor, which then converts it back into an electrical signal. In this way, both analog and digital signals can be transmitted, and up to high frequencies, with complete electrical isolation between the input and output. This isolating function is particularly important for microelectronics, in the periphery of microprocessors. This is where you find keypads, sensors, transmission lines, power switches, motors, electromagnetic valves working with quite different potentials. Optocouplers are reliable in preventing any mutual influence and keeping all potential-related interference away from the sensitive microprocessor. A major characteristic of an optocoupler is its coupling factor. This tells you how high the output signal is for an input signal of a given strength. Good optocouplers achieve coupling factors of more than 1 to 1. Between the input and the output, depending on the model, there may be differences in potential of several kilovolts. A speciality of Siemens optocouplers is the transparent ion screen of silicon, known as TRIOS, on the receiver chip. This ensures that signals are not corrupted by field effects if the isolation load is long-term. Optocouplers are small, so they are just right for applications demanding high packing density. One optocoupler does not even weigh a gram. Their small size and wide frequency range make them far superior to relays and transformers in many an application. Here we are looking at the manufacturing process. In the optocoupler, an infrared radiating gallium arsenide luminescence diode is used as the transmitter, and a silicon phototransistor as the receiver. A light-conducting medium produces the optical coupling link. Finally, this functional unit is given a plastic package to protect it against light and other sources of disturbance. Optocouplers come in two forms, in a DIL6 or a DIL4 package. Both have their advantages. The DIL6 coupler offers an accessible base terminal on the phototransistor. The DIL4 coupler requires less space, so it enables you to achieve substantially greater packing density. Both versions are available for conventional board insertion or for surface mounting. The end product, a small, unassuming device. But it has to live up to exacting demands, which is why every step in its creation is watched over by a quality assurance system that leaves nothing to chance. Inspection of raw materials, mechanical, electrical, climatic stress tests, a 100% final examination, item by item. User experience from system technicians in other parts of Siemens is drawn on. Experience from office communications, data and automation engineering. This helps to further improve the design, the production techniques, and the testing methods. Approvals and certificates attest to the reliability and safety of Siemens optocouplers. These are often the first requisite before an optocoupler may be used in applications where operating reliability is quite vital. Example, automation. Microprocessors control machine tools by means of sensors, switches, motors, valves with quite different operating voltages. Optocouplers protect the sensitive microelectronic devices and prevent any mutual interference in the periphery. They work in the same manner in process control systems, data memories, laser printers. Example, power supply. Microelectronically controlled switch mode supplies power office machines and computer systems. Optocouplers reliably isolate the low voltage and line circuits. Example, electronic signal box. Here, optocouplers keep interference in the traction current circuit away from the controller. Thus, the electronic circuits are securely guarded. Corruption of the signals and the danger this can entail are eliminated. And every train reaches its destination quite safely. Automation, power, railway safety. These few examples prove that microelectronics needs optocouplers of ultimate dependability, and millions of them. The source? Siemens, of course. Fiber optics are becoming an increasingly important medium for the transmission of information in industry and telecommunications. Large bandwidth, immunity to interference, absence of electric fields, and reliability of service, even on long transmission routes, are the reasons why systems planners are increasingly deciding to use optical waveguides. For this innovative technology, Siemens already supplies a wide range of components: connectors, couplers, converters, relays, transmitters, and receivers. The efficiency of optical waveguides in service is crucially dependent on the choice of the correct individual components. A coherent system philosophy is thus central to Siemens' development. To meet the special requirements of high-speed data transmission over optical waveguides, there is a complete family of components, the 200 megabaud system from Siemens. This family represents optical waveguide transmission in top form. The heart of this system consists of specially developed optical transmitters and receivers contained in a hermetically sealed dual inline package. The monolithic integrated circuits inside the modules ensure the utmost dependability. Huge investments have been made right from the start in research and development with the object of achieving an extremely high level of integration. This guarantees that the most stringent requirements in terms of reliability and service life are met. The module is of compact design with 20 pins beneath the package, enabling it to be soldered directly onto circuit boards. A 2.5mm DIN connector, or one which meets the SMA standard if requested by the customer, is used to connect the optical waveguide. Optical fibers with core diameters of 50, 62.5 or 85 micrometers can be used with these connectors. Both the transmitter input and receiver output are ECL 100K compatible. This laser transmitter can be used for transmission distances of up to around 20 kilometers and has electrical inputs compatible with the transmitter module just shown. The laser transmitter is installed in a metal case with heat sink and can be soldered directly onto circuit boards. The data transmission rate of the entire system is set by this clock oscillator and can be up to 200 megabaud. This device operates at standard frequencies of 125 and 200 megahertz. Customer-specified frequencies between 100 and 200 megahertz can be provided upon request. Full compatibility with ECL 100K is achieved with the aid of this parallel-to-serial converter. This converts data from parallel into serial format for the optical transmitter. A clock recovery on the receiver side extracts the clock signal for the serial-to-parallel converter. The clock recovery module uses a surface acoustic wave filter as the frequency selective component. A serial-to-parallel converter converts incoming data received in serial form by the optical receiver into a 16-bit parallel data stream. The converter also has a monitor function, monitoring it for correct operation. The parallel-to-serial and serial-to-parallel converter is contained in a single package. Optical transmitter and receiver, clock oscillator, clock recovery, and the converter. 5 members of a high-performance family of modules from Siemens for optical waveguide transmission at rates of up to 200 megabits per second. The growing volume of information handled daily in large-scale computer systems brings the planners of office and industrial complexes up against enormous problems of rapid and reliable transportation of data. An extremely effective solution to this problem is provided by the 200 megabaud transmission system from Siemens. Here, an optical data link with a high modulation rate finds practical application as a bidirectional link between computers. This is the interface. The components of the optical waveguide transmission family are integrated on the printed circuit board. The optical transmitters and receivers of this system operate at a wavelength of around 1,300 nanometers. This guarantees that when the standard transmitter of this system is used with a 50 or 62.5 micrometer duplex fiber, a distance of at least 3 kilometers can be spanned without signal distortion. Their large transmission bandwidth and complete immunity to interference make optical fibers absolutely ideal for applications in modern office communications. The 200 megabaud transmission system from Siemens can also be used in all present network structures according to individual customer specifications. Multi-computer systems are not, however, the only field where this family of optical waveguide components show their superiority. Their special advantages are also demonstrated in the transmission of high-speed data between input and output peripheral systems. In this case, a laser printer is equipped with the optical waveguide interface of this system. Transmission rates of 200 megabits per second make for an extremely high output of hard copies. Monitoring with the aid of video cameras is playing an increasingly large part in industrial process control systems. Transmission of the video signal over long routes using traditional technology requires considerable outlay for shielding and signal processing. High immunity to interference, complete absence of voltage and low attenuation even on extremely long routes are the chief advantages of using optical waveguides. This is a typical application for the Siemens 200 megabaud system. The composite color video signal from the color camera is converted into an ECL-compatible digital signal and delivered to the optical transmission system. Camera control and remote control signals, and if necessary audio signals as well, can be included without problems. The laser transmitter used in this configuration ensures reliable transmission up to around 20 kilometers. In this way, reliable video monitoring systems can be built up, even for very large-scale industrial plants. Optical waveguide technology guarantees efficient data transmission. Examples from actual plant design provide clear evidence. The particular advantages of using optical fibers are also demonstrated in the fast, reliable transportation of data over long routes. For this innovative and cost-saving technology, Siemens already offers complete systems, advice and service throughout the world. Optical waveguide transmission in top form, the 200 megabaud system from Siemens.